Hello and welcome to this presentation about our ongoing work exploring the relationship between ventilation and the spread of airborne pathogens through the use of a system dynamics model and applied to the COVID-19 pandemic. This work is the result of an ongoing collaboration between the Copenhagen University Hospital and the Department of Public Health at the University of Copenhagen. The case is based on increasing evidence that COVID-19 is transmissible through air. Additionally, airborne pathogen transmissibility is dependent on viral concentration in the air. However, policy focus with respect to ventilation has been on distance guidelines such as the number of people in a room or indications like the 2-meter rule, the use of masks, and generic ventilation guidelines. Ventilation can, however, have an effect on airborne viral concentration. Therefore, there is a great opportunity to test scenarios for different indoor environments, exploring the possibility of activity-based ventilation, as the needs would not be the same for a school or a restaurant, for example. This scenario testing could identify ventilation system requirements such as airflow, required filter effectiveness, or relative humidity, for example. Or it could indicate suitable activity types and durations for existing ventilation systems. The first question we attempt to answer when developing this model is to understand the physics of the problem. There is a susceptible population which comes in contact with vira in the air within a room and eventually becomes infected. This infected population become producers of vira, which continue to accumulate in the room. This increases the density of vira in the room, resulting in the infection of other susceptibles, creating a vicious cycle of virus production and infection. Now consider a ventilation system. This ventilation system recirculates the air in the room, exchanging some of the air for fresh air outside, losing in the process viral particles. Additionally, due to gravity, ventilation currents, and deactivation, vira could be lost due to them settling on surfaces or becoming inactive. This results in a decrease of the number of infected over time. Our dynamic hypothesis, therefore, expects that higher ventilation levels will result in a lower transmission rate. The model is based on a basic SE susceptible exposed model with stocks for both susceptible and exposed populations, and a flow rate from susceptibles to exposed dependent on the number of vira inhaled, represented by quanta, a measure of viral concentration and infectivity, and the contagion effectiveness of this quanta. It is worth noting that in our model, the exposed population does not become infective, but rather there is an exogenous variable representing the infective persons in the room. The infected in the room produce infective quanta at a rate based on the individual quanta production that takes into consideration things like the infectivity of the pathogen, the vocal activity of the infected from whispering to singing loudly, for example, and the physical activity of the infected from sitting down to doing intense exercise. This quanta accumulate in the room and is reflected in the model as a stock, and has a direct effect on the quanta inhaled, closing the cycle of infection and virus production. The quanta inhaled also is dependent on the effectiveness of the masks, if these are used. However, this quanta stock in the room can also decrease as a result of a number of factors. In our model, we have the 4 most important factors according to multiple published sources. First is the quanta losses due to particles settling on surfaces as a result of gravity. Then the quanta losses due to particle deactivation, natural half-life, or ultraviolet light degradation, for example. Third is the losses due to ventilation air changes, where a fraction of the total ventilation air is fresh air, and therefore particles are lost there. And fourth is the quanta losses due to ventilation filters, such as physical barriers. Finally, our model represents a causal relationship between the infection rate and ventilation characteristics. As an initial application example, we have tested our model for some examples provided in literature. Here we show the case of a 25 square meter pharmacy where one infected person is present for 1 hour and where other 15 susceptibles are also present in the premises and do not leave the premises. With an air exchange of 0.2, low, and without the use of masks, the quanta concentration reaches a maximum of 0.06 quanta per cubic meter, and close to 8% of the people in the room would become infected. These numbers will change if, for example, the susceptibles are only in the pharmacy for a limited time, or if they wear masks, for example. Thank you for your time, and please contact us if you have any questions about this ongoing work.